Hey guys, welcome back to the fourth video in this Flame game development series where we are making Ski Master, a top-down vertical scroller about skiing. So in the last one, we created a very simple level and understood how the new camera system works. Using that info, we were able to set up an initial position for the camera. And now in this video, we are going to add the player character along with input handling code to control its movement. So let's start by first creating a new file called player.dart under the game folder. This will contain our player class which extends from position component. Position component derives from the component class and represents game objects with transformation data. This transform is essentially made up of translation, rotation, and scale of the object. This is perfect for the player because we want to be able to control the position, rotation, and scale of the player as the game progresses. So back in the onload of gameplay class, let's create an instance of player and add it as child of the world. By default, a position component does not have any visual information. So if I run this now, we won't be able to see any visual difference. But to verify the location of this component in the game, we can set its debug mode to true. If I run the game now and load a level, you'll notice that there is something rendering at the top right corner. Since we didn't specify a position for the player, it got placed at the origin of the world and all its debug information is getting displayed outside the camera's view. To fix this, we can expose the position of the player as an optional parameter in its constructor. This parameter actually comes from the base position component that player derives from. And that is why I have written it as super.position. Now back in the gameplay class, let's set the position of this player to 20,20. And if I restart the level, you can see that a point gets displayed at this coordinate. And if you haven't noticed it yet, Flame's coordinate system uses a flipped y-axis. This means the origin is at the top left corner and y values increase as we move downwards. This might seem a bit odd if you haven't worked with such a coordinate system before, but all I can say is get used to it. This is more common than you think in a lot of game engines and applications, especially when it comes to 2D layouts. Okay, now we have a player class in the game, but it is just a point. And even though a position component does not render anything by default, it can still have some children components that are responsible for visual elements. So in the player class, I'll create a private late final member of type sprite component called body. Sprite component is a special type of position component provided by Flame that can render a sprite or an image. So this body will store the visual information for the player. And to initialize this member, I'll override the onload method. Here, I'll set a new sprite component as the body. Sprite component has a lot of optional parameters that we can set, and one of them is sprite, which controls what gets rendered by this component. The sprite that I want for the player is in our image assets. So we'll have to first get hold of this image to set up the player sprite. Now, Flame has a standard way of loading and caching assets. And to make things even easier, the Flame game class already exposes the global asset, image, and audio cache. And to get a reference to the root game object in any of the downstream components, we can add the hasGame reference mixin to those components. This mixin exposes a getter called game, which can be safely accessed once the component starts loading. Note that hasGame reference is going to replace the old hasGame ref mixin in future. So try to avoid using the old one. Next, in the onload, we can now use game.images.load and load the tilemap underscore pack.png. I'll await for this and store the returned image as tiles. Now tiles will contain the whole image, but we just want a small portion of it for the player sprite. But luckily, most of the sprites in our image are of uniform sizes. This allows us to create a sprite sheet using this image with size of each sprite being 16 by 16. Sprite sheet sort of slices the given image into sprites of given size. It then allows us to easily access any of the sprite using its grid coordinates or its overall index. So for the sprite component, we can get the sprite directly from the sprite sheet by calling getSprite. And we can get the row and column for the player sprite by counting it in the image from the top left corner. So the sprite is at the 5th row and 10th column. Finally, we'll just have to add this body to the player component. This will ensure that whenever we move the player component, the body moves along with it. And if I restart the level, you can see that the player sprite is now displayed in the game. Now, if you are looking carefully, you might have already noticed that the body is not centered around the parent position component. To explain this better, let me zoom in on the level by reducing the fixed resolution. And let's also move the player so that it is visible through the camera. So here, you can see that the top left corner of the sprite is placed at the position we specified for the player. This will become more evident if I set the position for the player as the top center of the map and disable the debug mode. In a way, this means we are controlling the top left corner of the player and not the center. This will become challenging to work with if we start rotating and scaling the player. Ideally, one would expect the position to be the center of the player sprite. And we can easily do that by setting the anchor of the body of player to anchor.center. And now you can see that the sprite center matches the position we provided. I'll just move the player position down by 8 units so that it doesn't go out of the view. And don't worry about this magic number because in future videos, the start position in each level is going to be defined in the level itself. So this code is anyways going to change later. For now, let's reset the camera back to the original resolution. Okay, now there is one small problem with our image loading that I'd like to point out. Ideally, we should not have loaded this image here because the whole tile map also depends on this image. So if we are able to see the tile map, that means the image is already loaded by Flame. And since we haven't created our own image cache anywhere, this loaded image already gets cached in the global image cache. Now this image cache is smart enough to detect if we are trying to load an image that was already loaded. And in such cases, it just returns the cached image instead of loading it again. But unfortunately, in this particular case, it fails to detect that. And just to prove this, I'll place a breakpoint after the image has been loaded and then I'll restart the level. Now with the breakpoint hit, if we try to inspect game.images, you can see that its internal map indeed contains two entries. The first one is loaded by the tiled component and the second one is loaded by our code. Both of them are the same images, but the only difference is in their keys. By default, Flame uses the file name as the key for caching the images. So instead of loading the image again, we can just call game.images.fromCache and use the same key as the one used by the tiled component. And you can understand where this key comes from by opening the level1.tmx file. Here you can see that the path to the image is stored relative to the tmx file. Now back in the onload of player, we won't have to wait for the image here because it directly comes from the cache. And if I save this and restart the level, you can see that nothing fails and the player sprite is still visible. Okay, now to make the player move, we'll have to override the update method. All Flame components have this method which they can override when they want to execute some code on every frame of the game. And the DT input to this method is known as delta time or frame time. It is the time elapsed in seconds since the last call to this method. If I try to print it, you can see that its value keeps on fluctuating. For me, this stays roughly around 16 milliseconds, which means the game is updating at around 60 FPS. And this also means any code that you write in the update method will be dependent on the frame rate. This is not ideal because how frequently update is called per second depends on how good or bad the hardware is. So to change the position of player in the update method and still keep it independent of the frame rate, we'll have to make use of the delta time. If you think about it, when the frame rate is higher, delta time will be smaller, and if the frame rate is lower, the delta time will be higher. This means if we move the player based on how much time has elapsed since the last update, we will make the motion independent of the frame rate. So here I'll increase the y component of player's position by adding 10 times dt to it on every frame. And remember, I'm increasing y component because y increases as we move downwards. What I have written here is basically the simple equation of uniform linear motion. Speed is equal to distance upon time, or distance equal to speed multiplied by time. This means for every frame, we are just calculating the distance to be moved for that frame, assuming the speed is 10 units per second. And no surprise, if I save this, the player appears to be moving downwards at a constant speed. Now, to make the camera follow the player is very simple. For that, let's go to the onload of gameplay. Here, instead of moving the camera to a hard-coded position, we can set it to follow the player. And if I restart the level, you can see that the camera now moves along with the player. And you can also see that the pause menu actually does pause the game. Now back in the player class, let's refactor the movement logic to make it more flexible and dynamic. First, I'll introduce a new private vector too called move direction, which points in the downwards direction by default. The idea is to have this as an unit vector that represents the direction in which the player is moving at any given point. Then in the update method, we can use move direction to update both x and y components of the position. By default, this does not change anything and the player still moves downwards. But if I change the value of move direction to make it point diagonally towards down and right, you can see how the player's movement changes. So by changing the x component of move direction, we can steer the character left or right. We'll use this fact later while implementing the input handling. But for now, let's reset it back to 0, 1. In the update method, another way to update the position is by calling the add scaled method on position like this. Internally, it does the exact same thing. Next, instead of using the magic number 10 here, I'll create a private static const member called max speed and set it to 80. This works fine, but it looks a bit odd that the player just shoots at max speed right from the start. To fix that, let's introduce a private member called speed with its initial value as 0. I'd like the speed to increase gradually from 0 to max speed over a period of time. And we can easily do that by using the lerp double function. This function returns a linearly interpolated value from a to b at an interval of t, where t is 0 at a and 1 at b. So here, a will be current speed, b will be the max speed, and for t, I'll use zero point 0.5 times the delta time. Here, dt is used to keep the lerp frame rate independent. Lerp double can return null in some edge cases, which I'm not too much worried about. So I'll unconditionally cast the result and store it as the new speed. Now we can use speed instead of the max speed in the position calculations. And if I restart the level, you can see that the character gradually picks up speed. We can verify the same by printing the speed value to the console. Finally, since rate of change of velocity is known as acceleration, we can convert the point phi in lerp double into a static const called acceleration. Okay, now let's get started with the input handling to make the player steer. Although it is possible to write all the input handling code in the player class itself, I feel that it gives the player too much responsibility. Plus, it operates under the assumption that only a single game entity can be controlled by external inputs, which can be false if your game has multiple objects that the player can take control of during the gameplay. That is why I'll try to keep the input handling code decoupled from the player class. So first, let's create a new file called input.dart. This file will contain the input class that extends from component. And as we want to handle the keyboard inputs, I'll also add the keyboard handler mix into this class. Inside this class, I'll first create two private boolean members to track the state of left and right key presses. Then I'll override the onKey event method and update the values of left pressed and right pressed by checking for the appropriate key in the keys pressed set. And notice that I'm using left and right arrow keys as well as A and D keys here. Next, I'll create a public member called hAccess and set it to 0. This is what the external classes will access to get the current state of horizontal input. And to update the value of hAccess, I'll override the update method. In here, I'll always reset hAccess to 0 at the start and then will remove or add 1 to it based on the current state of left pressed and right pressed. Essentially, this means if the left key is pressed, h-axis will be -1, and if the right key is pressed, it will be +1. Now, this is not the final form of the input handling, but let's quickly test this to see how it looks in the game. So I'll go to the gameplay class and will create a public final member of type input. Then I'll add it as a child of the world. Next, in the player class, we'll have to get hold of the input component to access the value of h-axis. It is possible to store a direct reference to input component in player, but I'd like to avoid that. Instead, I'll add the has ancestor mixin of type gameplay to player class. This is sort of similar to the has game reference mixin, but instead of looking for an instance of gameplay upstream, it looks for a component of given type and exposes it as a getter called ancestor. But unlike has game reference, this getter can only be safely accessed while the component is mounted to the component tree. Okay, so in the update method of player, before using move direction to update the position, I'll set the x component of move direction as ancestor.input.hAccess. Now if I save this and restart the level, you can see that I can move the character horizontally using A and D keys. Right now, the movement feels too snappy as the direction change happens immediately. We'll address that in a moment, but let's first make sure the character is looking in the direction where it is traveling. This can be easily done by updating the angle of player with the screen angle of move direction vector. Okay, and it looks like the angle is offset by 180 degrees or pi radians here. So let's add pi to the screen angle before updating the player's angle. And now it looks correct. Okay, now let's go back to the input class and make the h-axis smoothly transition between left and right values. For that, I'll introduce two more private members called left input and right input with both initially set to 0. These will essentially represent the key strength of these keys. Then next, in the update, I'll remove everything and will add some code to make the left input and right input values lerp. The important difference here compared to the previous lerp calls is that I'm changing the target values for both the inputs based on their respective key press states. So for example, if the left key is pressed, the left input will gradually move towards 1. And if the left key is not pressed, the left input will gradually move towards 0. And the same goes for the right input. This will give us that smooth and curved motion when a key is pressed or released. And for the rate of lerp, I'll create a static const member called sensitivity. And finally, the h-axis will just be right input minus left input. This will automatically make the value of h-axis negative if the left input is more stronger than the right input. Now if I restart the level and try to make turns, you can see that the motion looks smooth and much more natural. Although it might not be visible in the video, but the player is actually able to move faster while it is making turns. This happens because the move direction of player is not really an unit vector, as its magnitude goes beyond 1 when its x component is non-zero. To fix this, I'll always set move direction's y component to 1 in the update and then will normalize the move direction. Doing so will ensure that move direction always has a magnitude of 1 and does not speed up the player. Okay, and this also allows us to increase the target values of left and right input in the input component so that it can be higher than 1. If I do that and restart the level, you can see that now the character has a slightly larger range of angle when it turns. Okay, now one last thing that I want to take care of in this video is the keyboard handler mixin that I added to the gameplay class. I originally did that because I wanted to handle the keyboard inputs for various on-press callbacks. But now that we have an input component, maybe we can delegate this task to that component. So first, let's go to the input class and add a final map with logical keyboard key as key and void callbacks as value. I'll name this as key callbacks. The plan is to allow other classes to set up callbacks for particular keys and let input component take care of the rest. Next, I'll add an optional parameter to the constructor of this class to set this map. And if it is not provided or is null, I'll set an empty map here. Then in the onKey event method, after updating the left and right key press states, I'll check if the current event is of type raw key down event. This is necessary because onKey event gets invoked for key down as well as key up events. Next, I'll also make sure that the event is not a repeat event. When a key is held down longer, multiple key down events are raised. In such cases, repeat is false only for the very first key down event. Rest of all will have the repeat as true. So this check will ensure that we don't invoke a callback multiple times while the same key is held down for longer. Inside this if block, I'll just loop through all the entries in the map and check if any key matches with the current event's logical key. If it does, I'll just invoke the callback for that entry. Now back in the gameplay class, we can create the key callbacks while creating the input component. I'll also convert these callbacks into required parameters as the callback for keys is non-nullable. An input will also have to be marked as late because we are trying to access another instance member while initializing it. Okay, and once the key callbacks are set up, we can get rid of the onKey event and the keyboard handler mixin completely from this class. One final thing that I'll change in the input class is that I'll make it stop handling keyboard events when the game is paused. For that, I'll first add the hasGameReference mixin to this class. Then in the onKey event method, I'll wrap everything inside a game.paused equal to false check. And everything should still be working as before without any errors. So if you want, you can play around with the various const parameters we added in this video and see how they affect the player handling. But anyways, that is all for this video. If you enjoyed it and learned something new, do hit that like button. Maybe also consider subscribing to show your support, and I'll see you in the next one.